and in this case is 179.165. This is the same as the result from the distance method, where we can pass the two positions of the points A and B, and the result would be exactly the same, 179.165. Even better, MaxScript recognizes nodes which always have a position in 3D space, and supplying only the nodes instead of their positions would still calculate the distance between the two nodes, between the pivot points, correctly and return exactly the same result. It is interesting to note that the vector, which is the subtraction from the vectors A and B, could be expressed as A minus B, and if we would add B to the vector A minus B, the minus B and the plus B would annihilate, and the result would be again the vector A. As we know, we start with the beginning of the first vector, then we add the second vector and connect the beginning of the first and the end of the second in order to get the sum. So we see that the subtraction of vectors is exactly the opposite to the vector addition. RGB color values in MaxScript can be easily converted into 0.3 values and can be seen as a special case of three-dimensional vectors. In fact, some of them can be even seen as four-dimensional vectors, since they have a fourth component, which is the alpha. The predefined color red is color 25500. That color as 0.3 value is expressed as rectangular brackets 25500. Note that colors that have an alpha value of 255, that means alpha is opaque, don't actually display the alpha, but if we would multiply the red by the scalar 0.5, we can see a fourth value, which is the alpha divided by 2. Instead of denoting points in 3D space, the color values denote points in color space, where the X, Y, and Z axes are replaced with red, green, and blue. At the origin, all three colors are 0, resulting in the color black, and at the point with coordinates 255, 255, 255, the resulting color is white. We could visualize this using the following script. We're going to create a box at every 25 units in color space. We're not going to create all 255 boxes along each color axis, because that would be too slow. So we define a step of 25 and create the first loop for the red color, going from 0 to 255 using the step. Then another loop for the green color with the same step, and a third loop for the blue color from 0 to 255 using the same step. And then for every iteration, we're going to create a box which has the size of the step, and the position defined by the R, G, and B variables from the loop, and the wireframe color using the same values. If we would evaluate this script, we're going to get an array of boxes representing the colors. Since the scene lighting currently is set to use lights, the default lights of 3ds Max, we can create a new light, disable that light, and then in the environment settings set the ambient light to pure white. This gives us a self-illuminated look. As you can see, at the origin we have the color black, and on the opposite side we have the color white with the red color running along the x-axis, the green color running along the y-axis, and the blue running along the z-axis. In fourth-dimensional space, there would be a fourth axis representing the alpha. Obviously, we cannot represent easily four-dimensional space in three-dimensional space, so that's going to be left to pure mathematics. Most other vector operations, like scalar multiplication, as we saw before, and vector additions and subtractions, can be performed with colors, just like with normal 0.3 values. For example, let's create a sphere and set the wire color of this sphere to the predefined color red. Then add green to the red. The result is the sum of the two colors. We can ignore the alpha because it's not used in this case anyway. And then we could even multiply the resulting color vector with a scalar in order to get a less intense yellow color. We can of course mix in blue, which gives us a gray value, or we can mix the blue after the multiplication. So we can use color values just like we use 0.3 values. We can multiply them, add them, and subtract them.